Alright, so we're going to finish off the exponential functions unit by looking at applications and word problems. So a couple things you need to look at before we start going into that. Just to recap, when we're looking at a parent function, so one of the form f of x equals a to the x, so no transformations done to it, just the plain parent function. Whether the function models growth, so it's increasing, or models decay, or is decreasing, depends on the base. So if the base of the function of the parent function is greater than 1, we have something that represents growth. And if the base of the function is between 0 and 1, we model decay. Okay, you can't have a base that is negative. So the base is either going to be between 0 and 1, in which case it models decay, or a decreasing exponential function, or it'll be greater than 1, which models growth. And just to confirm that, we can take a look on Desmos here. There's two graphs right here. We have y equals 1.2 to the x, so we see the base is larger than 1, and it's exponential growth. And we have a blue one here, y equals 0.7 to the x, which is decreasing, modeling exponential decay. And as you can see, the base there is less than 1, 0.7. Okay, so, however, when we're solving word problems, it's not going to be just the parent function. We also might have a c value out in here. Instead of just y equals a to the x, it'll be y equals c times a to the x. This will be the basic equation that we're going to use to model any problem we do that's going to involve exponential growth or decay. So I'm going to look at a couple of different graphs here. And I want you to see if you can see a connection between the value of c in the equation. So in this case, the value of c is 2500. In the second graph here, the value of c is 1000. And in the third case here, the value of c is 5000. So take a look at the graphs here and see if some of these c values sort of stand out as being something specific on their respective graphs. Okay, so what do you think c might represent in this type of situation? Okay, so you might be able to see it from these graphs, but if it's not clear, let's take a look at the graphs on Desmos. It can be a little bit clearer. So if I have y equals 2500 times 0.5 to the x, again, this c value here is 2500. So looking on the graph here, what does 2500 mean? Well, it's actually the y-intercept. Okay, see if that's the case for all the other ones. So if I bring in the blue one here, y equals 1000 times 2 to the x, again, my y-intercept is 1000. And for the last one, 5000 times 1.05 to the x, again, you'll see again that my y-intercept is 5000. So the c value here is always going to be the y-intercept of the equation. You could also think of it as the initial value, because if x was representing time, when time was 0, we'd have a y value of 5000. So consider the initial value of the equation as well. Okay, so in general, if you're going to look at our exponential equation, y equals c times a to the x, so c will be your initial value, okay, also the y-intercept of the graph. X and y are your two variables that you're going to be using inside the equation. So x is usually time or a certain number of growth periods. Okay, so you have something growing or decaying over a certain period, and so x will represent that time or the number of periods. Y will then be the final amount. Okay, so after a certain amount of time and a certain initial amount, the y value would be the final amount, and a would be the base of our exponent. So it could represent growth or it could represent decay. Again, we're going to know what represents growth if it is larger than 1. It will represent decay if it is smaller than 1. Okay, and if we have a growth rate, that's usually something we add or subtract. If it's a growth rate, we're going to add it to 1. Decay rate, we're going to subtract it from 1, again, to model growth or decay. Okay, we'll look at some examples of that coming up. Now, in general, when we're talking about growth rates, they're given to you in percentages, and if you want to put it into an equation, you have to convert it from a percentage to a decimal value first in order for it to make sense. Okay, so again, we'll do some examples working with this base and seeing what we can do with it, just so we can become a bit more familiar with it. So here, we're going to ask you to determine the percentage change, and I'm giving you the base. So the exponential function, we don't know the initial value or anything like that. We're told the base of the exponential function is 1.24. So right away, when I look at this, I see a base of 1.24 that is larger than 1. So I know right away this is going to represent exponential growth. Okay, this is going to be an increasing exponential based on what I see here. Okay, so if it's growing, my growth rate is going to be r here. So since I'm growing, it's going to be 1 plus my growth rate, and my growth rate here, well, is going to be whatever I add to 1 to get 1.24. So technically here I have 1 plus r equals 1.24. I need to solve for my growth rate. So I'm going to subtract 1 from both sides of the equation here. So I wind up with r equals 0.24. Okay, so my growth rate is 0.24. Now how do I put that into a percentage? Well, I multiply it by 100, so this is going to be 24%. Okay, so meaning that if you have a base in your exponential of 1.24, it represents growth by 24%. Okay, so looking over at B, now we have 0.81. Now this base is now less than 1, so it's going to represent decay or a decreasing exponential. Okay, so if it represents decay, we're going to subtract our decay rate from 1 to get our base. So knowing that our base is 0.81, 1 minus our decay rate is going to be equal to 0.81. Okay, and again, we're solving for the rate, the r. So I'll subtract 0.81, I get 1 minus 0.81. Okay, I add r to both sides to get r over here, and I wind up with 0.19. Okay, so it's decaying, so it's a decay rate of 0.19, which when I turn into a percentage is going to be 19%. So I have 19% decay, represented by a base of 0.81. Okay, so this one's one I'm going to give you to try on your own first. So this is asking to find the point of intersection between these two graphs. And I know we could try and solve it graphically, but if we're trying to find the point of intersection between any two lines, you can use substitution. So back in grade 10, you've set these equations equal to each other. We have y equals y equals. So we have 2, 1 over 5 to the negative 2x equals 10 times 25 to 3x plus 5. Okay, so what we actually have is an exponential equation. So remember, when we want to solve any exponential equation, our goal is to get both sides of the equation under a single power with the same base so we can equate the exponents. So I'll let you try that on your own first, and I'll run through the solution quickly when you're ready. Okay, so first thing you want to do is check your answer. You should get negative 11 over 4. So what I did first to try and get the single power on both sides of the equation, I divided both sides of the equation by 2. So left side stays the same. I wind up with 10 divided by 2, which gives me 5. And then notice that 1 over 5, 5, and 25 can be written as powers of 5. So I replaced 1/5 with 5 to the negative 1. Okay, sorry, a little typo here. This should still be a negative. Okay, 5 to the negative 1 to the exponent negative 2x. Then 5 is obviously 5 to the exponent 1, and 25 I rewrote as 5 squared. So I just simplified with the exponents. I multiplied power of a power here, so I have negative 1 times negative 2x give me positive 2x for my exponent on the left. And then I multiplied 2 times 3x plus 5 to get 6x plus 10 for my exponent on the second 5 on the right. So then on the right side, I still had to multiply these two powers together, so I added the exponents. 1 plus 6x plus 10 is 6x plus 11. And then I have my goal, right? I have a single power on both sides of the equation, so I can equate the exponents. So I end up with 2x being equal to 6x plus 11, which I then solve to get x being negative 11 over 4. Okay, so once you determine that you're trying to find the point of intersection, you can equate the two equations, and then it becomes a situation very, very similar to what we saw back in lesson 26. Okay, so now let's look at a more typical type of application problem. So we want to know what amount of money would grow to $2,500 in 6 years if invested at 9% per year. So if you haven't seen this notation here, 9%/a, this just means 9% per annum, okay, which really just means 9% per year. So we want to know what amount of money would grow to $2,500 in 6 years if we invested at 9% a year. So as a rule, when you have one of these word problems with exponential functions, we can start off by saying y equals c times a to the x. Okay, that's the general equation we're going to be using to set up word problems. So the trick comes trying to figure out what represents each variable in the equation from what's going on in the word problem. So we know from our chart from a few slides ago that c represents our initial value. So we want to know what amount of money would grow to $2,500 in 6 years and invest at 9% a year. So the amount of money that we're looking to grow, that's what we don't know. That's our initial value. So that's actually going to be our c. So our c here is completely unknown. That's going to be our missing variable. Okay. Now we want it to grow to $2,500. So our final amount, which is our y, is going to be $2,500. So we're starting with something we don't know. That's c. We want it to grow to $2,500. It's going to take 6 years. Okay, so that's our time value, so that's going to be our x. Okay, and we invest at 9% a year. Now, you got to be careful here. This investment is going to grow at 9% a year. We do not put in that 9%, 0.09 as our base. Why? Well, this is clearly less than 1. So if you put that into the equation for a, that's going to look like it's exponential decay. When this is clearly going to be growing because it's going to be gaining interest each year. So our growth rate is 9%, which we turn into a decimal. But since it is growth, we're going to add it to 1. So our base is going to be 1 plus 0.09, which is equal to 1.09. Okay, so this base of 1.09 represents growth of 9%. So once we have all this, we can throw it into the equation. So our y value is 2,500. Our c is unknown. Our base is 1.09. And our exponent 6. Okay, and once we have this, it's just a matter of using algebra to solve for our missing variable. So I have 2,500 equals c times 1.09 to the 6th. It's going to be tempting to run 1.09 to the 6 into the calculator. However, I'm going to ask you not to do that because it's going to be an ugly decimal, and if you round at any point, you're going to lose a ton of accuracy. Okay, so you want to be very, very careful with that. So what I'm going to ask you to do is to do this all in one step in your calculator. First, I'm going to do some algebra. I'm going to divide both sides of the equation by 1.09 to the exponent 6. Okay, so now I'm just left with c equals 2,500 divided by 1.09 to the exponent 6. Okay, and you can run all this through your calculator in one step. Okay, when you run it through your calculator, you should wind up with an initial value for c of $1,490.67. Alright, so that's our first word problem. There's going to be a whole bunch more over the course of this lesson. Okay, so I'd like you to think about this one. I just want to ask you to set it up on your own first. Try and figure out what goes where, and then we can run through the algebra for it together. But at least try to set up the equation. So as always, you're going to start with y equals c times a to the x, and from the equation, I want you to figure out what goes where inside the equation, and then go forward from there. Okay, so when you have it set up, push play again, and we'll go through it together. Okay, so to figure out what goes on, goes where inside this formula, inside this equation here, we're looking for the annual interest rate. So to know the annual interest rate, we need to know the base of the exponent. The base of the power, which means that a is actually going to be our unknown here. Now, we're starting off with an investment of $1,150. We want it to grow to 1306.95. So our starting value c is 1150. Our final value y is 1306.95. And it takes 4 years, so that becomes our x value. So you can throw all that into the equation. Okay, so some a value we don't know to the exponent 4. Okay, so the algebra for here is a little bit different than the last one, obviously, because we're solving for a different variable. So we're trying to isolate for a and divide both sides of the equation by 1150. Okay, and again, don't round it. Keep things exact as long as you possibly can, because any kind of rounding can very quickly lead to a very inaccurate answer. Okay, and that's going to be equal to a to the exponent 4. Okay, so we've run into this kind of situation before where we have an unknown in the base of a power and we have an exponent on top of it. So if this was a squared, well, you would take the square root of both sides. Well, this is a to the 4th, so we're actually going to take the 4th root of each side in order to get a by itself. Okay, so we wind up with a being, technically it would be plus or minus because it's an even root that we're taking. The negative one would be inadmissible. But when we run that through your calculator, you should get about 1.0325. Now remember, we actually want the interest rate. So our a is actually equal to 1 plus my growth rate. Okay, so to actually get my interest rate, I need to subtract 1 from this. So I get 0.0325 is equal to my growth rate, which to convert to a percentage, I'm going to multiply by 100. So you should wind up with 3.25, or round to one decimal place, 3.3%. Okay, we're going to continue this in part 2 of the lesson. We'll see you over there.